In part 2 of Mod 7b, we are going to continue talking about polynomials. First, we need to define some terms. The degree of a polynomial is the highest power on a variable in that polynomial. The leading coefficient of a polynomial is the coefficient of the term with the highest power in the polynomial. We can learn about the end behaviors of a polynomial function by looking at the degree of the polynomial and the leading coefficient. The first possibility is the degree of the polynomial is odd and the leading coefficient is negative. If this is true, the graph rises to the left and falls to the right. So it could look something like this. If the degree of the polynomial is odd and the leading coefficient is positive, the graph falls to the left and rises to the right. So it does the opposite of the first possibility. If the degree of the polynomial is even and the leading coefficient is negative, the graph falls on both ends. So it might look something like this. Our final possibility is if the degree of the polynomial is even and the leading coefficient is positive, the graph rises on both ends. So both ends will be going upward. Now that we've learned the rules about end behaviors, we're going to look at a polynomial function and decide how the ends would look. On this first function, our highest power is 3. So we have an odd degree. Our leading coefficient, the number in front of that, is negative. So we have a negative leading coefficient. When this happens, that means that your function will rise to the left, fall to the right. For this example, check and make sure that it is written in descending order, and it is. But be careful, every once in a while they will try to trick you a little bit and put the terms in a mixed up order. So our degree comes from our first term, and it's 4, which is an even number. So we have an even degree. Our coefficient on that term is positive. So we have a positive leading coefficient. When this happens, that means that both ends rise. Notice that on this function that we've been given, it is not completely multiplied out. So we have to figure out what the degree would be if it was completely multiplied out. Use each of the items that are being multiplied here to help you figure this out. We would have to take this 2x times, if we did the FOIL on this whole quantity, the highest power would come from taking the x times x, which would give us an x squared. And then we would have to take it times the highest power of x that appears here, which is x to the first. If we multiplied that out, we would get 2x to the fourth. Now that we have figured this out, we know that we have, looking at our highest power here, an even degree. And looking at its coefficient, we have a positive leading coefficient. When this happens, that means that it rises on both ends. In ALEKS, they will write it as rises, right, rises, left. You need to recognize that that means the same thing. On the last example using this idea, again, this function is not multiplied out. So if we took each factor and looked at it, from the first factor, we would have negative 3x squared. And if we multiplied out the quantity and squared it, the highest degree term would be an x squared. If we do that multiplication, we would have negative 3x to the fourth. So now, what's our degree? 4. So we have even degree. What's our leading coefficient? It's negative. So what does that mean for the end behaviors? That means that both ends fall. Which they will write in ALEKS as falls to the left, falls to the right. Earlier in this mod, we talked about multiplicity. Multiplicity tells us something about how the graph looks. When an x-intercept has odd multiplicity, the graph will cross the x-axis at that x-intercept. On the other hand, when an x-intercept has even multiplicity, the graph will touch the x-axis at that x-intercept. For our next examples, we are going to determine the end behaviors for the graph. After we do that, we are going to find the x-intercepts and whether the graph touches or crosses the x-axis at each intercept. For our first example, we have f of x equals the quantity of x minus 1 times the quantity of x minus 2 being squared times the quantity of x plus 1 being squared. So remember that that first quantity has a power of 1 on it. If you add all of those powers that you see, our degree would be 5. And because all of the quantities are positive, we would have positive leading coefficient. So if we have an odd degree and a positive leading coefficient, our ends fall to the left, rise to the right. The other thing we are supposed to do is find the intercepts and whether we touch or cross at each intercept. So let's find the x-intercepts. We're going to just set up a table here. We're going to think about the multiplicity for each one. And then we're going to decide based on that, will we touch or cross? Our first x-intercept comes from this first quantity. That x-intercept will be 1. The degree on it is 1, so its multiplicity is 1. And when the multiplicity is odd, you cross at that value. Our second x-intercept comes from our second quantity. It will be 2. The power on it is 2, so its multiplicity is 2. And when the multiplicity is even, you touch at that intercept. Our third intercept comes from our third quantity. It would be -1. The power on it is 2, so that's its multiplicity. And because it's even, we touch at that intercept. On this function, we have x times the quantity of x minus 2 being squared times the quantity of x plus 1. Keep in mind that that plain x, because there's nothing showing, it's understood to be a power of 1. And again, on the quantity x plus 1, because there's nothing showing, it's understood to be a power of 1. So our degree, if we add those powers, is 4. If we multiplied that all out, everything is positive, so we would have a positive leading coefficient. When our degree is even and you have a positive leading coefficient, your end behavior both will rise. Setting up a table, we're going to think about what the x-intercept is, what the multiplicity is for that x-intercept, and whether we touch or cross at that x-intercept. Because we have a variable on the front, we get an x-intercept of 0 out of that variable on the front. The power on that variable is 1, so the multiplicity is 1. When the multiplicity is odd, you cross. From the first quantity, we get an x-intercept of 2. The power on the quantity is 2, so that's its multiplicity. And when the multiplicity is even, you touch at that value. And then our second quantity gives us an x-intercept of -1. The power on that is 1, so that's its multiplicity. And because it's an odd multiplicity, we are going to cross at that x-intercept. On this example, we will be using the x-intercepts and their multiplicities and the end behaviors to determine which of the graphs goes with function g and which of the graphs goes with function h. So we are given 6 graphs, and then we are given that function g is 2x to the 4th minus 18x squared. So first, let's just look at the degree. The degree is 4. The leading coefficient is positive. If you have even degree, positive leading coefficient, you know that you rise on both ends. So by having that information, we can automatically cut out this graph, this graph, this graph, and this graph. Now we need to find the zeros or the x-intercepts of this by factoring this function. I'm going to pull out 2 and x squared because that's a common factor. If I take 2x to the 4th divided by 2x squared, I'm left with x squared. Negative 18x squared divided by 2x squared leaves me with minus 9. Note that that is a difference of squares. So this factors into 2x squared times x minus 3 times x plus 3. So now our zeros of this, or x-intercepts of this, from this first item, we're going to have an intercept of 0. From the first quantity, we're going to have an intercept of 3. From the second quantity, we're going to have an intercept of -3. The multiplicity of the 0 is 2. The multiplicity of +3 is 1. The multiplicity of -3 is also 1. At the x-intercept of 0, because it's even multiplicity, we are going to touch. At the x-intercept of 3, because it's odd multiplicity, we are going to cross. Same thing for the x-intercept of -3. We are going to cross. So which of the graphs have us touching at x equals 0 and crossing the x-axis at 3 and -3? That's happening on graph A. Here's where we are touching at 0. Here's where we are crossing at -3. Here's where we are crossing at +3. For function h, we are given x times the quantity of x squared minus 9. If we multiplied that out, the highest power we would have, taking this x to the first times the x squared, would give us an x to the third. So our degree is 3. Because both of these items are positive, we would have a positive leading coefficient. And when you have odd degree and positive leading coefficient, you fall to the left, rise to the right. So which of these graphs fall to the left and rise to the right? Well, these are both up. This is rising to the left, falling to the right. Graph C meets our requirement. Graph D meets our requirement. Graph E, both ends fall, so that can't be right. And graph F, both ends rise, so that can't be right. So now we are down to only graph C or graph D. To help us figure out which one we need, we want to factor this, find our x-intercepts, and where we touch or cross. Notice that your quantity is a difference of squares, so your function of h can be rewritten as x times x minus 3 times x plus 3. This means that our zeros, or our x-intercepts, they are the same thing, happen from the x out front. That would give us an x-intercept of 0. From the first quantity, we would get an x-intercept of +3. From the second quantity, we would get an x-intercept of -3. Now let's look at multiplicity and whether we touch or cross. Because the power on the x, which gave us the x-intercept of 0, is 1, its multiplicity is 1, which means that we will cross at that 0. For the x-intercept of 3, when you look at the quantity, the power is 1, so its multiplicity is 1, which means, again, we will cross at +3, and the same thing happens for -3. So going back to our two possibilities, when we look at graph C, here's -3, we are crossing. Here's 0, we are crossing. Here's +3, we are crossing. That works. Do we fall on the left and rise on the right? Yes. So graph C is the correct answer for that function. If you checked graph D, you cross at 0 and you touch at positive 3. That is not what we needed, so we know that can't be our answer.